Curvilinear coordinate systems 12. The u-v-z coordinates of an elliptical system are related to a set of Cartesian coordinates by this set of equations, and we're now going to do part A, sketch the lines of constant u and constant v on a two-dimensional xy grid. So I'm going to copy these equations here and set constant u is equal to u0. Okay, so I have a cosine hyperbolic u0 cosine v for x and a sine hyperbolic u0 sine v for y. So let's check these equations once again. Cosine hyperbolic cosine, sine hyperbolic sine. This is going to be two-dimensional. We will do it on an xy grid, so we don't worry about z in this case. Okay. Now, if I look at these equations, the first equation, I'm going to take the square of it and multiply it by sine hyperbolic square u0. So let's do that. Sine hyperbolic square u0 x square is equal to a square sine hyperbolic square u0 cosine hyperbolic square u0 and cosine square v. Now for y, I'm going to multiply it by cosine hyperbolic square u0 and take also the square of this equation. So I will have cosine hyperbolic square u0 y square is equal to a square sine hyperbolic square u0 cosine hyperbolic square u0 and sine square v. And let's add these two terms, these two expressions. Now I can see that I have the same prefactor for cosine square and sine square here. So if I add them up, I will have cosine square v plus sine square v multiplied by a square sine hyperbolic square u0 plus cosine multiplied by cosine hyperbolic square u0. And on the left-hand side, I will have sine hyperbolic square u0 x square plus cosine hyperbolic square u0 y square. So let's perform this addition. I have sine hyperbolic square u0 x square plus cosine hyperbolic square u0 y square is equal to a square sine hyperbolic square u0 cosine hyperbolic square u0. So what happened here? I got rid of the v dependence. All right. And if I divide it by cosine hyperbolic square u0, this equation, this actually becomes tangent hyperbolic square u0 x square plus y square is equal to a square sine hyperbolic square u0, and then I'm going to divide it by a square sine hyperbolic square u0. So you see this tangent hyperbolic is sine hyperbolic square divided by cosine hyperbolic square. If I divide it by sine hyperbolic square, only cosine hyperbolic will remain. So this will give me x square divided by a square cosine hyperbolic square u0 plus y square divided by a square sine hyperbolic square u0 is equal to 1. So I obtained this equation, which is describing to me an ellipse. So this is an ellipse. I recognize it as an ellipse centered at the origin, because this is x minus 0 squared, this is y minus 0 squared. So it is centered at the origin, the equation of an ellipse. With 2a cosine hyperbolic u0 and height 2a sine hyperbolic u0. In other words, one is the major axis length is a cosine hyperbolic u0, minor axis length is a sine hyperbolic u0. So this is basically a constant u surface, a constant u curve is an ellipse. Now for constant v case, I'm going to take this equation, square it and multiply it by sine squared v0. So for constant v is equal to v0, I'm going to get sine square v0 x squared is equal to a square cosine hyperbolic square u0 cosine square v0 and sine square v0. And for the y equation, I'm going to multiply the square of it with cosine square v0. So cosine square v0 y square is equal to a square sine hyperbolic square. This is u sine hyperbolic square u cosine square v0 sine square v0. So sine hyperbolic square, sine square, it was multiplied by cosine square, so that's here. And now I'm going to subtract the second equation from the first equation. So I will obtain, with this subtraction, sine square v0 x squared minus cosine square v0 y squared is equal to, now you can see that a squared cosine square v0 sine square v0 is common in these two. So I will have cosine hyperbolic square u minus sine hyperbolic square u, which is 1. So this will give me a squared cosine square v0 sine square v0. Okay, so if I divide it by a squared cosine square v0 sine square v0, x squared divided by a squared cosine square v0 minus y squared. So cosine squared is cancelled. I'm left with a squared sine square v0, and this is equal to 1. Now I have to recognize this equation. This is the equation of an hyperbola. So this it's x minus 0 and y minus 0 parentheses squared, which means it's centered at the origin. So this is describing a hyperbola centered at the origin. The vertices at x is equal to plus or minus a cosine v0, co-vertices at y is equal to plus or minus a sine v0, and we have a square cosine square v0 plus a square sine square v0 is equal to a square. So the focus points, the foci are at plus or minus a. Okay. So I have described the constant u and constant v curves on the xy grid. So for constant u, I've taken x and y equations, squared them, and multiplied the x equation with sine hyperbolic square and y equation with cosine hyperbolic square. Adding them up, I have cosine square v sine square v with the same prefactor. So it becomes cosine square plus sine square, which is 1. So I'm left with this prefactor here, and this is going to be sine hyperbolic square u0 x square plus cosine hyperbolic square u0 y square. Dividing this with this, I'm going to get rid of sine hyperbolic square, so I will have x squared divided by a square cosine hyperbolic square. Dividing this term with this, cosine hyperbolic square cancels. I have y squared divided by a square sine hyperbolic square. This is equal to 1, which is describing an ellipse centered at the origin with width 2a cosine hyperbolic u0, height 2a sine hyperbolic u0. For constant v surfaces, I squared the x equation and multiplied by sine square v0, and then I squared the y equation multiplied by cosine square v0. So that's here, and this one is here. Now I notice that I have a square cosine square v0 sine square v0, a square cosine square v0 sine square v0, the same prefactors for cosine hyperbolic square and sine hyperbolic square. So I subtract the second equation from the first because I know cosine hyperbolic square minus sine hyperbolic square is equal to 1. So this I have used many times. So that gives me sine square v0 x square minus y cosine square v0 y square equals to right hand side with this cosine hyperbolic square minus sine hyperbolic square being 1. And dividing the left hand side with the right hand side, I obtain the equation of a hyperbola centered at the origin with vertices plus or minus a cosine v0, co-vertices plus or minus a sine v0, and focus points at a. Okay, now if I plot these using Mathematica, I can set a is equal to 1, and I can try different u values from 0.01 to 1.6, and this can be plotted with a contour plot. So this is x squared divided by a squared cosine hyperbolic square plus y squared divided by a squared sine hyperbolic square minus 1 equals to 0. That's the equation. So when I use the contour plot and show them together, I see that I'm getting these ellipses. So this is the x-axis, this is the y-axis, and you can see that this is u is equal to 0.01, this is u is equal to 1.6. So this is getting bigger and bigger as u increases. Now for constant v surfaces, I do the same thing, set a is equal to 1 and v is equal to a constant, and this time I have x squared divided by a squared cosine square v0 minus y squared divided by a squared sine square v0 minus 1 equals to 0. These are hyperbolas you can see here, and this is basically v is equal to 0.01, this is v is equal to 1.6. And we have the others in between. We can also show them together in a single plot. This is the x-axis, y-axis. So on the xy grid, these are constant u surfaces which are ellipses, and these are constant b surfaces which are the hyperbolas that we have described.